So let me give you the infomercial for the next 5 minutes of why I think this is a cool technique, and I hope we find some applications for it. So here is my problem. This is the pitch, right, for every good infomercial. Don't you have this problem every single day of your life? You've taken a spectrum and you need to calibrate it. And so if you have done any sort of like old school long slit spectroscopy, you probably are going to spend a little bit of time looking at an image like this. This is an arc lamp. This is a helium neon, I think at the same time, arc lamp from a 3.5 meter telescope that I know and love so well. And I've spent many hours of my life staring at images like this and figuring how am I going to figure out what the wavelength calibration of this image is. Now this is a very well solved problem, and I think familiar to many of us. All right, so you're going to, that's just the arc lamp. There's going to be some line that we call the trace that goes through this image, which traces out where the starlight goes. So you would probably take your star spectrum, map where that starlight falls on the chip. The x-axis is nominally the wavelength, but we don't know that solution. And then hopefully that line is very straight, and hopefully it is very flat or nearly flat. And so this is what you're trying to figure out. Which pixel is which wavelength? This is the model that we need to solve. This is the problem that we're trying to solve with 1D spectroscopy. So you take that trace, you extract the flux along that line, and then you might end up with a one-dimensional spectrum that looks something like this. So this is an emission lamp spectrum. Again, this is a problem familiar to many people. You have this series of lines, and you would like to know what lines are these. Again, you probably turned on the helium or the neon lamps. You have some prior because you turned the lamp on. You have a good idea of what lines those are supposed to be, what elements they are. But you need to know what emission lines those are. Okay, so there's metadata you need, especially if you're inheriting some data from another telescope, from another user, what lamp was on, what were the instrument settings, right? Which grading was in, what position was it in. All these things give you some idea of what you should be looking at. Which catalog for the lamps are you using or for the line list are you using. And then the traditional process is you would do manual identification. You would look at the lines and name them or pick them out. And the goal, right, this is the model we're trying to fit, and this is my kind of model, with apologies to the previous speakers who do much more complicated modeling. I want to fit nominally a straight line. This is my kind of modeling. We want to know how to turn pixel into wavelength. This is all we want. It is a simple problem, well described for a long time. So again, the manual solution that I think many of us grew up doing or are familiar with is looking at these lines and like clicking on them using some GUI, some interactive interface. This is the most well-tested, and I would argue, best interface that has ever been developed, IRAF. Nobody has beat it yet. For all of its problems, it is a very, very robust software suite that has solved this problem since the 90s. You would click on lines, look up some table, and say, okay, I think that is the such and such wavelength line, and then you'd type it in. And then once you had enough of those, you could fit some kind of linear or polynomial model. Once you had that model, you could then go to the next spectrum in the night and use re-identify, which just does some sort of cross-correlation, slides the solution around, updates it in real time. This is a very well-tested workflow. But I am very lazy. I do not want to click on lines. I don't want to have to select them because I am lazy, because I have a hard time copying things down correctly. I am very error-prone to typing in numbers, and I think we only usually pick the biggest lines. There's lots more features in these lamps than the giant emission lines that you could use to calibrate this. And so if only there was some method to do this automatically. Can we do this automatically? Yeah, absolutely. I am not the first person in the last 40 years to come up with this idea. In fact, IRAF in the 90s had a couple of good solutions that were tried. This has been done. I'm going to introduce today a method that I borrowed from computer science called dynamic time warping. Now, this is a relatively classic algorithm in the computer science world. It was used in the 70s to pave the way for speech recognition. And so the example I like to give is how do you take the waveform from the word space and fit it to a sample of somebody saying space, right? You stretch out a vowel, the pacing is changed. You need to take that model, that waveform, and dynamically stretch it. What if you have a nonlinear stretch? So here's an example, kind of a cartoon example from some kind of emission lamp-like thing where you have some reference and then it's been non-linearly stretched over the pixel values, and it goes pixel by pixel and it figures out how to do that alignment. Now here's another representation of this. If you had, this is the same kind of plot. You're trying to figure out this warping path, which in our case is the wavelength solution we want, right? It transforms from pixel space into wavelength space. So what if this is highly nonlinear? What if this has discontinuities in it, for example? Or what if you just don't know where you're supposed to be looking? This has been used a little bit in astronomy, and this is the best use case I have found. There's a couple others, but this is the best one of taking models of the solar wind and stretching them in time and seeing if you can reproduce the actual values you got. So I want to give a little bit of love. I'm not the first person to use this algorithm. Here is an example of a very, very naughty spectral calibration that we created. So one of those is the model, one of those is the actual quote-unquote data. It's a model of the model. And we did a bunch of horrible things. We made a nonlinear solution. We put a break in it. There's discontinuity in it. The lamp lines are all random. There's different noise properties. One of the lamps is off in this case, so we have the wrong model slightly. And what we can do is you can go through and stretch it. And you can find all the little circles here represent the little emission line peaks that we then found. That you can see that it did a good job. Good. So this is my advertisement that my code works. Here's a real example from a real spectrum. This is a medium resolution spectrum on top that we observed, and then on the bottom is the low resolution template of the same lamps. And we can solve it. It does a good job. There are many limitations to this algorithm. It's not a silver bullet here in terms of solving this problem, but it does a very good job, and I'm happy to talk about some of these limitations. I would say my biggest takeaway is it's not a good solution for extreme precision RVs. It does not replace the need to do laser frequency combs or something like that. But you can pip install a piece of software called PyCosmos, which we wrote to use the Cosmos spectrograph on the APO 3.5 meter. And we have put this as a feature inside of PyCosmos. And I hope you all give it a try. I think it's a good, easy way to do at least a reasonable job of one-dimensional wavelength solutions. And I hope you give it a try and break my code for me. Thank you.